So welcome you to this India Plus lecture series, and welcome everyone. So in the past few weeks, we are discussing the flow and its fluctuation from different heavy ion experiments. So in the past weeks, we had a talk from STAR collaboration and CMS collaboration. So today we have Professor Zhou from Niels Bohr Institute, and he'll be talking about go beyond the standard anisotropic flow study at the LHC. So the general rule is that we have about an hour of seminar, and unless you have any pressing question, we usually take those at the end of the talk. But if you have anything very urgent, you can raise your hand and then speak up. Yeah, I think that's mostly we have as a general introduction. So anything else, Sandeep or Rishi?
No, I guess that's all. Yeah.
So yeah, so if we have the recording and other stuff going, then I think we can get started, right?
Yeah, it is already started, sir. 2 minutes before.
Okay. Thank you. So you can take it over.
Okay, great. Well, first of all, it's my great pleasure to meet you all here, and I try to discuss I believe this is a lecture, so I try to cover the flow activities, especially with the ALICE results. So if you have a quick question, I guess we can stop immediately in the slide. Otherwise, I suggest that we have a discussion in the end. So today I will talk about go beyond the standard flow analysis at the LHC. And firstly, so I want to show you this picture which made by our students, which briefly illustrates the evolution of the Big Bang. So by smashing heavy ion collisions at nearly speed of light at the LHC, you can create a very hot and dense matter called quark-gluon plasma. And shortly after the formation of quark-gluon plasma, the quarks and gluons will form hadrons, which interact with each other until a certain time called freeze out. And then the particle escape from the system and can be catched by the detector, such as ALICE. This would have been done in experimental side, while from the theory side, for different stages of the heavy ion collisions, there are different dedicated models to simulate each phase. We have a different initial state model for the initial conditions. We also have a hydrodynamic model, a parton transport model for the system dynamic evolution. And then in the end, we also have final state calculation, which can be compared to the experimental measurements. And by such a data and model comparison, we try to extract the information about the quark-gluon plasma. And that is perhaps one of the most important goals of the relativistic heavy ion collisions at the LHC. And then anisotropic flow is one of the key observables, which you already know from all the previous speakers, that it's a very powerful tool to study the quark-gluon plasma. An idea has also have been illustrated explained by Sergey and also the other speakers. So I just briefly mentioned here that for non-central heavy ion collisions, you have this overlapped region, which shows like this American football shape. This spatial eccentricity in the initial state will be converted into the momental space anisotropic particle expansion, which is known as an elliptic flow, which proposed by Shang-Yi Olitor back in 1992, so 1 year ago. And what we know is that the size of elliptic flow will reflect the initial eccentricity, which is defined here, and also reflect the information of the transport product of the quark-gluon plasma. Okay, this is the simple picture which has been established back in 1992. However, the reality is more complicated due to the event-by-event nucleon distribution inside of the nuclei. We have not only the eccentricity, but also have the higher order anisotropic coefficient, such as epsilon 3, epsilon 4. And then this initial state anisotropy can be converted into the final state anisotropic flow, quantified by the flow coefficient, V2 for the elliptic flow, V3 for the triangular flow, etc., etc. And then in the final state, instead of just use the flow coefficient V2 to describe the particle expansion, we have the online probability density function in terms of Vn coefficient, Vn, Vn, Vk, and also the corresponding flow symmetry plan, such as psi m, psi n, psi k. And what we do is, so the study of the joint probability density function, the PDF, is very, very complicated. So what we usually do is we do the projection to a certain direction, and we try to study For example, how does the flow coefficient Vn fluctuate event by event? And how does the flow symmetry plane fluctuate in different kinematics? And also we want to study how do the flow coefficient correlate with each other, different Vn and Vn, how do they correlate it? And how do the flow symmetry plane correlate it between psi n and psi n, for example? So with these 4 different directions, we can actually simplify the study for the PDF in certain direction. And before we go to the complicated one, let's start from the simple definition of flow. So the Vn is defined as a visual angle of the produced particle with respect to a certain symmetry plane. However, in experiments, the psi n is unknown. So what we do, and what we hope that we can do, is using a 2-particle azimuthal correlation. So when you correlate one particle with the other, if you do a simple math, which it will give you the Vn square, which means you can obtain the RMS value of the Vn distribution without knowing the flow symmetry plane of psi n. This is what we hope to have in theory. While in reality, what we really get is from the 2-particle azimuthal correlation is basically the Vn square plus additional contribution or contamination called non-flow effect, such as resonance decay jets. And I believe Sergey already explained in the previous lecture what is non-flow and how to suppress non-flow. And one of the powerful ways is using the multi-particle correlation or multi-particle cumulant. So for example, here we are talking about the 4-particle cumulant for Vn. And then what we do is we first pick up a 4-particle correlation. So you randomly pick up a 4-particle from the event, and then you subtract the correlation between the internal correlation. For example, here you have phi 1, phi 2 with phi 3, phi 4. We subtract the correlation between phi 1, phi 4, phi 2, phi 3, or phi 1, phi 3, phi 2, phi 4, which are the combination of 2-particle correlation. And then you can see for the all 4-particle correlation, we subtract all the lower order 2-particle correlation. And in the end, you only have Vn to the power 4 plus a non-flow combination of the 4-particle. And then, as you can see, this is basically a non-flow that's coming from 4-particle. And resonance decay, which decay into 2-particle, will not really affect this measurement. So in that sense, by using the 4-particle cumulants, you can largely suppress the non-flow combinations in experiments. And similarly, we can also do the multi-particle cumulants, V2-6 with 6-particle or V2-8 with 8-particle cumulants to measure the flow coefficient. And they can largely suppress the non-flow as well. So now we can assume that for Gaussian fluctuation, when the flow fluctuation is much smaller than the Vn coefficient, we have roughly Vn square equals to the Vn square for the flow from the flow symmetry plane plus the flow fluctuations plus our non-flow contamination. While all the 4-particle, 6-particle, 8-particle cumulant, high-order cumulant, basically have a different sensitivity to the flow fluctuation. It's a minus, so the Vn square minus the sigma V square. So this is important because if you can suppress the non-flow effect also in a 2-particle correlation using something like eta gap method, then by using the combination of 2 and 4-particle cumulant, we can obtain both the Vn coefficient and also the flow fluctuation sigma V. Okay, so we will move on, and this is the measurements at the LHC. In the left-hand side is the first flow measurement at the top energy, 5.02 TeV in the lead collisions, which I show you the centrality dependent of V2 in the red, V3 in blue, and V4 in green. And on top of the LHC measurements, we also have the theoretical model prediction from the hydrodynamic model, where you can see a very good agreement between the two. And similarly, in the right-hand side, I show you the first measurements in xenon-xenon collision of the Vn coefficient as function centrality, where you also show a very good agreement up to 50% centrality. So this good agreement between data and model predictions, or from hydrodynamic model predictions, confirm that the quark-gluon plasma reproduced at the top LHC energy also behaves like a perfect fluid with an extremely small viscosity. And then I mentioned also, as you can see here in the picture, we, in addition to the flow with two particle correlation, we also have the V24, V26, and V28. So how can we use such information? By using the entire longitude data, Alice managed to measure the V24, 6, and 8 in a very narrow centrality bin, 1 or 2%. And then by using a different order of multi-particle cumulants, we can reconstruct the different moments of the VN distribution. And based on the moment, we can also reconstruct the event by event VN distribution, which is shown in the top right. So why this is important? Because if you assume the Vn, like V2, V3, they are proportional to initial set eccentricity, V epsilon 2 and epsilon 3, then you would expect that the normalized Vn distribution, so the Vn divided by the mean Vn, will be almost identical to the initial set eccentricity distribution, epsilon n divided by the mean epsilon n. And this has been confirmed also in the hydrodynamic model calculations. If you compare the P-Vn distribution to the P eccentricity distribution, they are almost identical. So this is very useful in the sense that we can use the final state P-Vn distribution to directly constrain our initial state models without worrying so much about the eta-vest and the viscosity of the quark-gluon plasma. And then, in fact, we also developed a new method which allows you to make V2 with 10 particle, 12 particle, 14 particle, or even 16 particle cumulant if you want. And this has been all implemented for the high Newman LHC, which is coming. So this is the Vn coefficient of the charged particle as function of centrality. And in Alice, we did far more than that. So for example, last year, we also submitted a paper based on the V2 of identified particle with 2 particle cumulant in the left-hand side, and even the 4 particle cumulant, the V24 in the right-hand side. So compared to the standard 2 particle correlation, the V24 can largely suppress the non-flow, especially at high PT. So therefore, when you compare to the model, I would say the V24 is more reliable and with less bias for non-flow effect. So what we can see here is that if you look at the PT below 3 GeV, there's a clear mass dependence, which means for pion, which has the smallest mass, its V2 is the largest. And then when you go to kaon and proton and lambda and until omega, when the mass increase, the V2 decrease at the same PT region. And this has been, in fact, observed before with a 2 particle or with an event plan method. And now we can confirm it with a 4 particle cumulant. While if you move to PT above 3 GeV, and you can see there are 2 different groups. The bluish points, they are the V2 of the baryon for proton, lambda, xi, and omega. And the other group in red, they are the V2 of meson. So we can see a clear baryon-meson grouping effect. So what I didn't show you here, but we had in this paper is a comparison to a hybrid model called LBT, which is a combination of hydrodynamics plus quark coalescence plus jet fragmentation. They can describe the data extremely well up to a very high PT. And this is the first time, and there's one model that can describe the entire data from low to high PT. But I will come back later on. And then for some of you who knows about the identified particle flow measurements, a popular way to look at the data or try to extract the further information is by looking at the number of constituent quark scanning. And the idea is rather simple. So for baryon, we know it has 3 constituent quark, and for meson, it has 2. And it was expected if the flow is carried by the protons or by the quarks, then one would naively expect a kind of a number of constituent quark scanning if you do V2 divided by NQ versus PT divided by NQ. And this kind of NCQ scanning has been confirmed at RIC back in 2005 by Starr and by Phoenix at RIC. And now we also want to confirm this picture at the LHC with a 4 particle cumulant, which is free of non-flow. And what we can see here is there is no universal scanning. The baryon V2, for example, 20 to 30% in the middle top. The red curve are the baryon and the meson flow, and after scanning, it is significantly higher than the band of baryon shown in blue. It's basically the same everywhere, and we do not see a universal scanning. I think at the moment there's no question that there is a platonic collectivity that has been produced, or there's a deconfined QGP matter that has been produced at the LHC. And now you will ask why there is QGP and there's no universal scanning of this NCQ scanning. Is it because NCQ scanning, the idea itself is too simplified, that shouldn't be used directly to probe the platonic collectivity? Or we shouldn't say, if you see NCQ scanning, that means platonic collectivity. If you don't see, that means no platonic collectivity. And a similar question should be asked or should be reconsidered at the RIG-BS program, when you say, okay, can we use the number of constituent quark scanning to search for the critical point if you start to see the NCQ scanning broken at low energy, because it's also broken at high energy, right? Then with for the flow measurements with 2 and 4 particle cumulant, we can use such an idea that 2 particle cumulant equals Vn square plus flow fluctuation, while 4 particle cumulant equals the flow Vn square minus the flow fluctuation. Then you can study the flow fluctuation by looking at V24 divided by V22, or by looking at the so-called relative flow fluctuation, which is roughly sigma over V. And this has been done as a function of transverse momentum for identified particle, ion and cation and proton. And if the flow fluctuation is completely driven by initial state eccentricity fluctuation, then one would naively expect a completely flat distribution in PT and no particle species dependent. And as you can see here in the right-hand side in the Alice paper, we show you that, first of all, it's not completely flat, there's a non-trivial PT dependent. And in addition, there's a clear particle species dependent. So here the blue is a proton, which is different from the red pion and cation. It's the same in the V24 divided by V22, or in FV2, the relative flow fluctuation, which just tell you that the flow fluctuation in the final state receive the contribution not only from the initial eccentricity fluctuation, but also modified by the system dynamic evolution, which give you non-trivial PT dependent and PID dependent. And for details, you can also read this paper, which has been accepted by JHEP. And then, so we also have the fluctuation of the flow symmetry plane. So the psi n has been used for most of the calculation if you want to do the Vn. However, we realize that for the initial participant plane, it will be converted to a different flow symmetry plane depending on the kinematics. So when you have a different PT, the low PT and high PT, the flow symmetry plane might be different. And because of the complication, I will not go through the details here. And I just want to show you that there are 3 slides about this very, very complicated measurement that we will not have time to discuss in detail today, but I refer to the following paper in Alice. And the conclusion is rather simple, that we can confirm in Alice with more than 5 sigma effect of such additional fluctuation of the flow symmetry plane versus PT. And then we can do something else. So in the previous slides, I mentioned that we can measure flow with 2 particle correlation in such a way. So you may basically doing this cosine 2 phi n phi 1 minus n phi 2 to get a Vn square. And also you can do the flow with 4 particle correlation, which give you n phi 1 plus n phi 2 minus n phi 3 minus n phi 4, which in the end you get a Vn power 4. And you ask why we only do 2 and 4 particle, why it has to be the same n, the same harmonic. Can I mix them? And one other idea you can do is, oh, now I have the 4 particle, there's also 4 particle cumulant that have been introduced before, that you can do a 4 particle correlation minus 2 types of 2 particle correlation, which give you the Vn power 4 to power 4. And one, so if we mix the harmonic, we use different harmonics for these 4 particle cumulants. What can we get? So now we start from cosine n phi 1 plus n phi 2 minus n phi 3 minus n phi 4. So if you want to get something which is completely non-trivial and non-zero, you need to make sure that all these coefficients n minus n will be 0 in the end. And this is an example. You have a n plus n minus m minus n. So it will be 0. And what we get in the end is something called Vn square times Vn square, take the average. And then you can subtract a correlation called Vn square, take the mean, and times Vn square, take the mean. But why it is useful? Because if there's no correlation between different flow coefficients, then you would expect that this observable symmetric cumulants will be 0. And if you see a non-zero result, and because this is a 4-particle cumulant, so it shouldn't be affected by the non-flow effect, let's just tell you there's a non-trivial correlation between different flow coefficients. And this measurement has been published in PLL as an edited suggestion back in 2016. So what we can see here is the red point is a symmetric cumulant, the normalized symmetric cumulant. So you also do a symmetric cumulant normalized by the flow coefficient as a function of centrality. And the red points clearly show you there's a positive correlation between V2 and V4, which means for a single event, when your V2 is larger than the event average V2, then your V4 will also be larger than event average V4. While for the blue point, it's a measurement of the correlation between V2 and V3, and you can see it's a negative value, which means they are anti-correlated between V2 and V3. In that sense, for a single event, if your V2 is larger than the event average V2, your V3 will be smaller than the event average V3. And in addition to the measurement itself, we also compare to the hydrodynamic model calculations. And in particular, we show you different different dashed lines, which represent the same initial state model using EKRT, but with different viscosity, the different eta of s as a function of temperature. And you can see for the correlation between V2 and V3, it is very, very sensitive to the eta of s as a function of temperature. So even all these hydro curves, they represent a calculation that can describe V2, V3, and V4 simultaneously. They cannot describe the correlation between V2 and V4. Okay. So that really means that with this new idea of symmetric cumulant, we can strongly constrain the viscosity as a function of temperature for the quark-gluon plasma. And then the other part is the blue one, the correlation between V2 and V3. And you can find that they are actually insensitive to the eta of s as a function of temperature. So it doesn't matter what is the eta of s of the quark-gluon plasma, the correlation are the same. And then what's going on? You might wonder. And later on, we also did this hydrodynamic calculation using different initial state model, Glauber, KLN, and AMPT initial condition, which go through with different eta of s for the hydrodynamic model calculation. And you can find that up to centrality 30 to 40%, there's rough agreement between the calculation with eta of s equal to 0.08 or 0.16. And this is not a surprise in a sense, because we are talking about linear response. So V2 is linearly correlated with eccentricity epsilon 2, and V3 is linearly correlated with epsilon 3. Therefore, if you use such a linear response, you would expect that the final state correlation between V2 and V3 will be equivalent or approximate at least to the initial state epsilon 2, epsilon 3 correlations. And that is also very useful in a sense we can use the measurements of symmetric cumulant shown in the left-hand side to directly constrain your initial state model by constraining the correlations between the epsilon 2 and epsilon 3, which is not easily accessed by the other flow measurements. And furthermore, you might wonder, what is the general correlation between any order of Vn coefficient or with many different flow coefficients? And one of these, this is only possible now with the so-called generic algorithm with multi-particle cumulant we published 2 years ago. This is basically a paper with very simple C++ code that allows you to do any multi-particle correlation, any multi-particle cumulant. And one of the examples is that you can use you can construct your own 6-particle cumulant to study the correlation between V2, V3, and V4. So different from the previous slide that you only look at the correlation between 2 harmonics, you can look at the correlation between 3 different harmonics, V2, V3, and V4. And this has been done also in Alice 2 years ago. Again, in the left-hand side, I show you the measurements of the very similar to the mixed harmonic, very similar to the asymmetric cumulants. Now we relate to the mixed harmonic cumulants. So the red is a V2V4 correlation, but right now measured at 5.02 TeV, which we have a much more data than at lower energy. So you can see the measurements is very, very precise. And the blue is again the anti-correlation between V2 and V3 that we discussed in the previous slide. But on top of that, we have the new measurements in green, which is the correlation between V2, V3, and V4. So it's actually quite interesting to see that these results is more consistent to V2, V4 correlation in central collision, and then go down and go to a negative and start to follow the correlation between V2 and V3. And this is clearly a non-trivial correlation between the three different flow coefficients. And when you compare to the model calculation that can describe, again, V2, V3, V4 as function centrality, they failed quite a bit when you compare to the new observable. So for example, if you talk about this AMPT, i.e. by Vishnu hydrodynamic model calculation using AMPT initial condition, they can describe V2, V3, V4 as function centrality, right? But then this new observable works quite okay for the AMPT calculation, while the Trento could not describe the data. It's underestimated the correlation by more than 50% if you look at the ratio here. Okay. They show it by these red shadows. So that basically shows us that by looking at this high order correlation between three different flow coefficients, we can actually have a stronger constraints on the viscosity of the quark-gluon plasma. And now we move to the correlation between flow symmetry plane. And don't be scared by this concept. Let me guide you through the simple math again. So we talk about two-particle correlation, right? You have the n phi 1 minus n phi 2, or you have four-particle correlation n1 plus n2, n phi 2 minus n phi 3 minus n phi 4. It's two and four-particle correlation. And how about three-particle correlation? Can I do something like k phi 1 plus n phi 2 minus n phi 3? And in fact, you can, but it can be trivial. So if k plus n doesn't equal n, then this observable will be 0 due to the symmetry. And this is something you can either check if you are doing, if you are from experiment, or if you are doing model calculation, you can just run it. You will find the results will be 0 due to the symmetry. But what if k plus n equals n? Then you can extend the cosine term and insert the psi. And in the end, you get the Vk times Vm times Vn and times cosine term of this guy. And it might be complicated, so let's put some examples. So let's say k equals 2, m equals 2, and n equals 4. So what will we have? Now we do a three-particle correlation with 2 phi 1 plus 2 phi 2 minus 4 phi 3. And that will give you a V2 square times the V4 times the cosine 4 psi 2 minus 4 psi 4, which is very useful because it will give you the correlations between different order flow symmetry planes. So if you can find some way to cancel out the flow coefficient, that will give you a direct measurement of the flow symmetry plane correlations. And some of the idea has been presented here in this PLB paper and also initially made by Alice in this PLB paper roughly 6 years ago. And let's check one of the latest measurements at the top LHC energy. So here, the rho 422 basically is using the three-particle correlation that I mentioned earlier that give you the cosine, the 4 psi 4 minus 4 psi 2. And we can see, for example, here in the top left, the results increase as a function of centrality. And what does it mean? It means in central collision, there's almost no geometry. Therefore, there's no strong correlation between psi 2 and psi 4. They are randomly distributed, therefore no strong correlation. But if you go to very, very peripheral collision, there's a clear American football shape, right? And then there's a clear psi 2 and psi 4, because the geometry tend to agree with psi 2 or align with psi 2, which give you a very strong correlation between psi 2 and psi 4. And when psi 2 and psi 4 is very close to each other, it will be cosine 0, which give you 1. And that is what we see in more peripheral collision for the Rho 422. And in addition, because of the high acidics, in Alice, we also do correlation between psi 235, psi 6, psi 2, etc., etc. And we can show you that with this new flow symmetry plane correlation, psi n, psi k correlation, we can constrain different hydrodynamic models. And clearly, one of the model with a Trento initial condition doesn't really work very well for this flow symmetry plane correlation. And then how can we combine the information? So here, well, there are different model calculation, which we call the Bayesian analysis. So what would they try to do is they include as much data as possible for the particle spectra or particle yield, mean PT fluctuation, as also as the Vn coefficient as function centrality, done by this Duke group. And they can do the global fits and extract the initial condition as well as the viscosity of the quark-gluon plasma. So here is the eta west, the shear viscosity over entropy density ratio as function temperature. And in the right, there's the bulk viscosity as function temperature. And similar work has been done 2 years ago by Jess Grape collaboration, but now they also include I think that the study of the PID, so of identified particle, so the mean PT of a pion, mean PT of proton. And they can also help you to extract the viscosity of quark-gluon plasma and also the initial conditions. And then later on, for both group in Uvascula and also in Netherlands, they try to include more and more flow observable to see what is the advantage. And what they find is when you include the normalized symmetric cumulus of NSE32, you have a better constraint on the initial condition. When you include the correlation between the higher order, V2, V4, V3, V4, you have a better sensitivity to the initial conditions. And similar work has been done by our Dutch colleague, who also included the PID flow as a function of PT. And they believe they can better constrain the viscosity of the quark-gluon plasma and also initial conditions. But now here comes the problem. There are different models for the initial state. And then depending on the hydrodynamic model and depends on the Bayesian approach, you get quite different initial state that you can constrain using experimental data. Right, so now if you just look at the situation last year in 2022, if you are using IP plasma initial condition, the initial entropy density is like this. While if you are using Trento calculation for the Bayesian analysis from Trediton, they look like this. And they are very different. You can judge already by eye. And then the question for us is how can we access the initial condition in experiment? And how can we improve our understanding on the initial conditions? And one of the idea is the following. So before we talk about flow, in the last 20 slides, we talk about flow and the anisotropic flow. The anisotropic flow will give us information about initial shape, the eccentricity, right? So if you have a small V2, it basically tells you if you have a small eccentricity. If you have a large V2, it has a larger eccentricity. And in fact, we also have the different measurements for mean PT, the mean transverse momentum of the produced particle, which is very sensitive to the system size. So if you have a small, for a certain number of events, a certain number of particles, if you have a fixed multiplicity, if you have a small mean PT, that means the size of the fireball is large. And if you have a large mean PT in the final state, you will know the size of the fireball is small. So how can we use such information? And it was proposed by Piotr Pozek that we can study the correlation between V2 and mean PT. If you do this, if you construct the correlate in such a way, which is very similar to the Pearson correlation coefficient. And this is defined in a way that cosine and this covariance is a 3-particle correlation with 2 particles for azimuth angle correlation, 1 particle for mean PT. And for the denominator, you have the flow fluctuation, sigma Vn, and also the fluctuation of mean PT. And we consider the Vn is proportional to epsilon n, right? So the initial and the final state Vn is proportional to initial state eccentricity. And mean PT is proportional to 1 over E, 1 over the energy density. Then you would expect that the correlation between Vn and MPT will be the same as the correlation between the initial state eccentricity and E0, the inverse. And this has been tested with a hydrodynamic model, either using Tredeton Bayesian calculation or VUSB hydro or Jetscape hydrodynamic calculations, which basically show you that there's a very good agreement between the initial state and the final state. And therefore, if you can do the measurements based on Vn and PT correlation, you can directly access the initial state eccentricity and E0 correlation. And this has been done by Alice and published last year. So what I show you here is a V2 mean PT correlation as function of centrality. The Alice measurements should present by this black point. And you can see there's a very weak centrality dependence. And this weak centrality dependence is correlatively described by the IP plasma plus music plus URQMD calculation. While all the rest calculation using Tredeton, Jetscape, VSB hydro, those are hydrodynamic model calculation from the Bayesian analysis, and they are all using the initial state model from Trento. And you can find they all show you a very strong centrality dependence, especially if you look at Jetscape, right? It shows a dramatic decreasing trend from center to peripheral collision, and they even change the sign to negative for centrality above maybe 20–30%. And this clearly deviates from the Alice data. So how can we understand the huge difference between IP plasma, hydrodynamic calculation, and the rest based on Trento initial state model? Is due to some CGC effect, which has been implemented in IP plasma. And then they also did an additional calculation with IP plasma, but now they switch off the contribution from color glass condensate. And you can see the results are actually agree with the calculation with the CGC. In another word, this agreement basically shows you that there's no CGC effect that has been observed here. And the difference between IP plasma and Trento calculation are not due to CGC, but some geometrical effect. So what is the geometrical effect? And it was realized right after right before the Alice publication that if you think about the different models, right? IP plasma is using the width of the nucleon of 0.4 Fermi, and the VUSB hydro use 0.5, and then Tredeton use 0.7, and Jetscape, which works the worst, use 1.1 Fermi for the nucleon width. And this actually follow the band if you think about the calculations, right? So because of the same idea, Giuliano and the collaborator quickly run the analysis and in using the IP plasma plus music plus URQMD, but this time within the same initial conditions, they are using completely different nucleon widths from 0.4 to 0.8 to 1.2. And you can clearly see that if you use 0.4, it's rather flat and follow the Alice data. And then if you use 1.2 Fermi for the nucleon width, it shows you a very strong centrality dependence, a dramatic decreasing trend, and change the sign in centrality 56%. So this basically explains that in order to describe the Alice data, a small nucleon width is preferred. And this is not a very well constrained before, unfortunately. And if you think about all the Bayesian analysis, like Jetscape and also Tredeton, they are doing an excellent job in describing the Vn coefficient and also mean PT, the spectra. However, they all failed in this calculation because of the very large nucleon width that has been used. And also for your interest, if you go back to the initial state calculation, here there's a small red ball which represents the size of the nucleon. And you can see back in 2016, it was very small. But then in Ducat Bayesian analysis, they already used a very large nucleon width. And in Jetscape, it's even larger back in 2020 and back to 2021, which is around 1.1 Fermi. And now in 2022, the Tredeton calculation start to include the hadronic cross-section measurements and also the VMPT correlation. And they find that the nucleon width is actually very small. So this is what we know about initial condition. And we do have very unique sensitivity to the initial condition. In fact, I want to remind you that at the LHC, we have not only the collision between lead at 2.76 TeV and 5.02 TeV, we also have the collision of 8 hours of data taking between collisions of xenon 129. And different from lead, which is a round nuclei, it's like a ball. For xenon, it has a very special shape, what we call the deformed shape. So if you think about the lead, it's more like a spherical, while for xenon itself, it looks like American football. That means there will be you would expect a large eccentricity already in central collisions compared to the lead. Right, and then to test the idea, they can further study so-called triaxial structure. So if it's like American football shape, you can also have a prolate shape, which means you have a 2 short axes, R1, R2 are the same, but shorter than R3, or you can have a 2 long axes, which means R2, R3 are longer than R1. Or you can have the triaxial structure, which means X, Y, Z direction, they all have a different length. And then if you do the calculation for initial state profile, you can see the shapes are actually not the same, and which also means the final state flow will be different. And as you can imagine, we can also follow the following 4 category to study how does the Vn fluctuate, how does psi fluctuate, how do correlation between Vn and Vn show you, and how do psi correlate it. And I will just show you 2 very simple examples. I showed you before the centrality dependence of Vn, V2, and V3 in lead and xenon. Now we put them together. And the solid points are the calculation for the measurements of xenon, and you can see the results are actually, V2 results are higher than lead results in central collision, but then become smaller in more peripheral collision. And this is more obvious if you do the ratio between V2 from xenon and to V2 from lead. That's a strong enhancement. And in fact, in Alice, we can even zoom in to have such a measurements in a very fine centrality, 1 or 2% beam. And now you can even see the finer details. There's a crossing between V2 of lead and xenon around centrality 12 to 13%. So if you do the ratio, right, you can find there's a strong enhancement in xenon collision of the V2. And why this is important? So now we compare to the hydrodynamic model calculation using different deformation. So whether they assume the xenon is like a ball, or there's a deformed structure with beta 2 equal 0.18, which is coming from the low energy nuclear physics, right? And then you can find the red or pinkish shadow is an ipiglasma calculation with beta 2 equal 0.18 can describe the data and the Alice measurements so much better. And this gives you a very strong indication that, in fact, the xenon traveling at the speed of light also shows a deformed nuclear structure, and the beta 2 parameter is very similar to the lower energy, which is at the level of MEV. Okay, now we are talking about 10 to the power 6 difference in the energy scale, while they share the similar nuclear structure. And this is the simplest Vn measurement that we can do. And now we also have the measurements of V2 PT correlation. We can even do the ratio between the two. And now let's compare to the model calculation. I guess it's called the reddish shadow is a calculation with triaxial structure, which means X, Y, Z 3 axes are all different, or compared to the prolate shape, which means you have 2 short axes and 1 long axis. And you can find the Alice data point clearly prefer the nuclear structure with triaxial. And this is actually the very first confirmation of the triaxial structure of xenon 129 at the LHC energy. And that, in fact, it also gave us a big hope that we might have a new connection between the high energy heavy ion collisions to the low energy nuclear structure physics. Because when you're talking about a nuclear structure at lower energy, I guess those physicists will tell you the structure they study is based on the charge radii, right? And for the nucleon distribution, they cannot really probe. While for the LHC, we can actually see both. And the exciting part is in the coming or the current LHC round 3 program, we are expecting to operate the collision between oxygen and oxygen collision. Why this is very exciting? Because instead of the standard Wood-Saxon distribution that describes the nucleon distribution inside of the oxygen, the low-energy nuclear series will tell you that the oxygen will look like in this alpha clustering structure. So instead of randomly distribute the nucleon, they start to have the alpha cluster inside of the oxygen, while the exact location of the alpha clustering is not completely clear right now, even for low energy. And if you also talk to a high energy physicist, they might tell you there will be a significant contribution from the color class condensate coming from QCD effective theory. So the CGC matter has been predicted by the effective theory since a long time, but hasn't been observed anywhere with the direct evidence. And it was hoped that we can also use coming oxygen-oxygen collisions to study the potential CGC contribution in the initial state. So I can tell you that in Alice collaboration, we have a lot of projection study for flow, including the VN coefficient, the correlation between VN coefficient, the PID flow with 4 particle cumulants, as well as VN as function PT. And in particular, it was predicted by the series that if you expect a CGC appeared in oxygen-oxygen collision, you would expect this correlation between V2 and V3 will change the sign twice. And the blue points basically show you the position of the coming LHC data. It will basically confirm that if you have the oxygen data as we expect, we can have a very large chance to identify or find the first indication of the CGC that appeared at the LHC energy. So I also want to share with you that, in fact, there are many discussions about nuclear structure at RIG and the LHC. In particular, if we consider the isobaron at the RIG between zirconium and rubidium. And in the past, just 1 year, there are many workshops and dedicated meetings on the discussion of nuclear structure in the key laboratory, including BNL, GSI, SACLE, and INT. And here are the links to these conferences. And if you have interest, please take a look. And now we move to a slightly different angle, to small system. All the previous slide, we talked about heavy ion, very heavy. So we create a hot and dense matter. We want to study the quark-gluon plasma, or we want to probe the initial conditions. And how about small system? In particular, if you consider that for collision between protons, for example, you also have a very small chance, less than 0.1% of the events, that also produce roughly 100 particles, which is similar to the very peripheral light collision. And naively, already for many years, we will say the proton-proton collision is like a reference data service for the QTP study. Well, the QTP in principle is not expected to be produced. But there are many surprises that have been observed. And here I want to quickly show you that in the CERN Yellow Report published in 2018, there's an extensive list which include almost all the possible flow analysis that has been done in heavy ion collision and hasn't been done in proton lead, and many of these are missing in the proton-proton collision. And this is also connected to what we discussed before. How does VN fluctuate? How does the psi fluctuate? And how do VN correlate with VM? And how do psi correlate with psi? And those are missing. And this missing part is not because we don't want to do it, because we have limited data for the LHC round 2 program. And now, as most of you know, LHC round 3 was started already. And we will have much faster data taken, especially in Alice. So that I would say the LHC round 3 will enable a new possibility with many times more data compared to round 2. And I hope some of you will have interest to finish the missing part in this table. I will just quickly show you the 2 examples for the flow measurements at round 2. So here what we have is the V2, V3, V4, again, as function uncharged of the motricity. And then let's focus on low motricity region. Well, the uncharged is below 200. And we can see the V2 here in lead is a bit higher than P lead, it's a bit higher than the PP. But already for PP, And P-lead sorry, is not so much smaller than lead-lead. Right? And also, if you look at V3, they are almost compatible in PP, P-lead with lead-lead. And similarly for V4, which confirms there's an observation of the flow already in small collision systems, including both P-lead and PP collisions. And the magnitude are very similar with heavy ion collisions. And this is particularly interesting because these measurements will challenge two paradigms at once. First of all, we want to see how far down in the system size does our standard model for heavy ion physics, the hydrodynamic, remain. And already from this picture, you can see the IP plasma that works fairly well in heavy ion collision. They actually couldn't describe the data extremely well. They show you a decreasing trend as function uncharged, which is different from data. And in addition, we want to understand, can the standard tool for minimum bias PP, our PCR model, remain the standard for the high multiplicity PP events? And I would just want to remind you that these PP events is the top 0.1% most central collision in proton-proton collisions. And it's really nice to see that our standard tool PCR model actually failed quite a bit in describing these Alice data. And we can take another example. This is a flow of identified particle. And I want to remind you, in heavy ion collisions, we see this mass dependence at low PT, and we see the baryon-methyl grouping effect at intermediate PT, which basically show you the QTP effects. And now we move to proton-lead collision and proton-proton collision. And the measurements in proton-lead and proton-proton is very challenging because of the huge non-flow effect. So when the number of produced particles is very limited, let's say below 100, the non-flow will be significant compared to the lead-lead collision. So what we do in Alice is we are using the unique coverage in eta, using this FMD detector, the forward multiplicity detector, which allows us to have the two particle correlation with delta eta almost up to 8, or here up to 7. And this is very powerful to suppress the non-flow effect if you combine with some non-flow suppression method using template fit, for example. So here I show you the V2 of identified particle using a long-range two-particle correlation with non-flow subtraction from a template fit method. And what we see is at low PT, there's a mass dependence for up to 3 GeV. So the pi on V2 is higher than the K on V2, higher than photon V2, higher than lambda V2. And then if you go to PT above 3 GeV, you start to see two groups. One is the baryon group, the V2 of proton and lambda are compatible, and they are significantly higher than the V2 of the meson band of pion, K0 and K charge. And similar results has been seen in proton collision. There's a mass dependence at low PT, while if you go to PT above 3 GeV, the proton V2 is significantly higher than the K1 and pion V2. So there's a clear similarity between the results in heavy ion collisions and also in small collision system. And if the baryon, if the mass dependence at low PT and baryon meson grouping in the medial PT can be taken as evidence of the platonic activity. So what is the indication we have here based on the similarity between PP, P-lead, and lead-lead? In order to confirm what we see, we also compare to the state-of-art model calculation, which is a hydrodynamic plus quark coalescence plus fragmentation model shown in the left-hand side. And here you can see in this model can describe the data fairly well. If I can even tell you that after further tuning of the eta of S, you can describe even the low PT part and also high PT part. And if you switch off the contribution from quark coalescence, right? If you don't have a quark coalescence mechanism, if you only have hydro plus fragmentation, you will find that if you go to PT above 3 GeV or 4 GeV, the model will significantly underestimate of the data and cannot describe proton V2 or pion K on V2. And this further confirms that we need the quark coalescence mechanism to describe the LHC data in small collision system, and therefore help us to believe that there's a discovery of the platonic activity in small collision system at the LHC. And this is one of the highlights in Alice back in 2000, back to Quark-Matter 2022. And I want to highlight that there's also new possibilities. So now if you think about the LHC running program, I'm not sure if this is the final, so caution of any further change. But we are going to take not only the proton-proton data, but also proton-oxygen and proton-lead. And this is really unique because if you think about the system size, and if you just look at a simple global initial or hydrogen initial state calculation, the geometry is not really the same. It's not completely decided by the proton, but also have some other impact that depends on the target, depend on the other side of the collision. So if you change from proton to oxygen to lead, the initial geometry is not really the same. It's not completely decided by the proton. So we hope that we can perform also kind of geometry scan at the LHC around 3, and we can better understand the initial conditions of the small collision system. And furthermore, we want to see if there's any possibility to understand the turn on and turn off of the QGP production in small collision systems. So that's bring me almost to the end. And here, instead of a summary, I want to show you in Alice. We just released the Alice review paper, which summarized the Alice activities or Alice results in the last 10 years. And in particular, for those within this blue shadow, those are the relevant flow measurements or flow discussions. So for your interest, please take a look. And after I finish the scientific part, I want to highlight the initial stage conference 2023 that we are organizing in Copenhagen this year. And I want to remind you that the abstract submission deadline is actually in 8 days from now. And in particular, we have the junior support for more than 50 students and postdocs. So if you have interest, please do consider to attend the conference, because we will pay the entire stay of the accommodation for a week during the conference. And we will have the reduced conference fee. And it's very relevant, and it's one of the largest heavy ion conference. So please don't miss it. And in the last slide, I hope I use 1 minute to advertise that we will open hopefully 2 PhD position and 1 postdoc position working in Alice in Copenhagen. And we have perhaps one of the best salary in the world for PhD and postdoc. So if you have an interest, please contact me for further information. Thanks for your attention.
Thank you for this very nice and comprehensive overview. So now the floor is open for questions.
Hi, can you hear me?
Yes.
Sure.
Hi, you. This is Samandat. Very nice talk. Thank you. Yeah. So if you, my question is like more general. If you go to slide, I think 23, or like even slide 7. Like it's more general in the sense that like all our like model predictions match very well with our data measurements in the central region. Like I think it was slide 16. I'm sorry. Yeah. 16. Yeah. Yeah. If you see, look at this 16. Yeah. Yes. So yeah, like in all our measurements, all the observables, the measurements match very well with the data predictions, mostly in very central region. And for almost all the observables, we see that the models deviate from the data towards the peripheral centrality, right? So in your opinion, like I just want to understand what do you think we are missing here? Like what might be happening? What might be like what we might be looking for, or like what can we do to address this particular difference in all the observables?
So I guess there was some confusion here. So there's no Alice data here in the right-hand side of calculation. So what we have, so the solid lines are the final state hydrodynamic model calculation, and the dashed line are what is it? No. So there's just one solid line and one dashed line, and when the dashed line represents a different, I mean, it's basically a different eta values, right? And
yeah.
the other is the initial state calculation within the same model. So there's no data model comparison here. It's within the same initial state model, with different eta overs.
I thought the plot on the left has like data points and the eta over s from different. So I thought it's from the final state model parameterizations, right?
So sorry. So you are talking about the left-hand side figure.
All right. Right. Yeah.
Okay. Yeah. Yeah. So what we know here is, for example, if you look at the blue one, right? This is based on the EKRT initial state of calculation, and well, what we know from here is basically eta over s doesn't matter for based on this model. Possibly due to the average eta over s is the same. So even they change the eta over s as a function of temperature, the average eta over s is kind of similar to 0.20. So that might explain why there's really no difference here. And I cannot answer what is missing in UKRT, because first of all, this is slightly different from the other model that we are using, like IP Plasma or Trento. For Trento, it's rather simple.
Sorry, so I just meant that in like any other like final state model calculations, even if you take like IP Plasma or anything like any state of the art model, right? You'll see that in towards the peripheral centralities, the models generally deviate from the data points almost all our like multi-particle correlation or like dominant observables, right? I was just asking like more in general, like, do you think we are missing something, or like if you can make some like, yeah. So in just your opinion on what we might be missing.
Yeah. So actually it's very hard to say, because if you asked me 2 years ago, I would say that the Bayesian analysis is very reliable, and they do extract the initial condition. And for example, here P equals 0 with Trento, which is similar to IP Plasma or EPRT. And at that time, I was convinced that this is one of the best we can do. But then you see, after this B2 PT correlation, it just destroyed my own whole confidence of the Bayesian analysis. And I would say, right now when we do Bayesian analysis, we can, because of the computing power, we can only include very limited observable, and we have to have a very careful selection of what we include in the Bayesian analysis. Because if you include, let's say, only VN and BT, it's just not sufficient to constrain the model. And when also before the Bayesian analysis, for hydro calculation, people just say, oh, now we have pick up T2, V2, we pick up the spectrum, let me fit. They try to find the best parameter and start to say this is eta over s, or this is initial condition. So I think right now in 2023, this is old-fashioned, and we shouldn't stay to that anymore.
Okay. All right. Thank you.
Oh, okay.
Yeah, I see hand raised from Yuri.
Yuri. Hello.
Yeah, hello. I hope you hear me. So you were showing this result about the PT V2 correlation, and I think it was the last slide you showed. Yeah, this one. So I'm wondering, basically, is there some kind of simple explanation why the correlation looks like that, and why the nucleon size matters in this correlation?
Yes. So depending on which way. So are you talking about these slides in 29 for the triaxial structure, or
no, the PT, you just keep scrolling. I'll tell you. the next one. Okay, this one, right, this one. No, not the nuclear structure one, the previous one.
Nuclear structure.
Yeah, this one. The difference in the epiglasma, etc. So is there some simple explanation why the width of the nucleon affects the correlation like it does?
I don't know if there's a really simple explanation, but so what we know, for example, is when you are doing the Bayesian analysis, they do some of them include mean PT as default, and one or two group also include mean PT fluctuation, but this is not sufficient. So if you want to study any further information, you need to also include high order correlation, let's say the third order PT correlation or PT fluctuation. In fact, our Alice Indian group, they are actually doing extremely well in this PT correlation. And here what we show you is the V2 PT correlation, also 3-particle correlation. And somehow if you go to higher order, they have much better sensitivity to the details of the initial condition. And in this particular calculation, you just see the nucleon width matter a lot. That this is not a big surprise because in the end, mean PT also give you the size, right? But it's beyond the mean PT and beyond the size, but also size fluctuations present here.
So I'm sorry to follow up. But, well,
sure, go ahead.
So basically what you're saying is that the smaller size gives you steeper initial density profiles. So you have the steeper, the faster radial flow development, and the mean PT is basically larger, right?
Yes, but remember for all these calculations, right? All the calculations present here, all of them can describe mean PT. So this is what I'm saying. So if you want to constrain initial condition, the size, it's not about mean PT itself. It's not only about the size itself. It's also about size fluctuations to the high order. And even for all the Bayesian analysis, or IP plasma, they include mean PT as a fit. They do not include the high order, or they only include the second order PT correlation, which is not sufficient to constrain the size. I guess that's a direct message I would say.
Okay, thanks.
If it's unclear, we can also have further discussion later, don't worry.
Hi, can I ask a question? This is Rajiv. Hi. You showed some plots of eta upon S as a function of temperature and zeta upon S as a function of temperature. Do you also have plots of eta upon S as a function of collision energy, root S?
That's a good question. So I don't know which energy. Remember, this rely on how much our series friends did, right? And for example, here they do the fit of the combined fit of that at 2.76 TeV and 5 TeV, because we believe that, or we hope the eta of S or the zeta of S will be almost the same as a function of temperature for the LHC energy. And I think there was some early work also at the top Rick energy, but as far as I know, unless I missed something, there haven't been any study for example, BES. It would be quite interesting to see if, when you do the BNN just scan results, whether they can also do the Bayesian analysis at different energy, and they can see different behavior. But I haven't seen any of this calculation yet.
Because I remember reading somewhere that the fluid at Rick is more perfect than that at LHC.
Oh yes, some early work, but that also depends on the tuning of the bulk viscosity, right? For example, if you think about the IP plasma, there have been significant improvements of the bulk viscosity, which was significant, which was very large. If I remember back in 1 or 2 years ago, and when I talked to Pension and beyond this year, they have a better tune of IP plasma. So I think there are many developments because of the cross section.
Okay.
So the cross section matter, the nucleon width matter, the bulk viscosity also matter. So in the end, everything is connected.
Okay, thank you.
But I fully agree that it would be quite interesting to have a full study also for the BES, and then suggest our series friends, for example, from JetScape collaboration, to fit the data. I do believe we have viewable data from STAR, and I think they should do that.
So you haven't seen such a plot, right? Eta upon S versus root S. Have you?
Sorry, I can.
No. Have you seen a plot of eta upon S versus collision energy?
No.
Okay. Okay.
Or if you know any, please share with me. I would be interested to know it.
Okay, so any other questions for you?
Hello, can I ask a question?
Yes.
Sure.
Yeah. So you showed the breaking of NCQ scaling at LHC energy. So what could be the reason of that? We do see that at rig the scaling holds. So why it breaks at LHC?
Thanks for asking this, because I think this is a very important question. And I fully believe that the NCQ scaling, the concept, has been used too widely, which is completely incorrect. And there are many papers which describe NCQ scanning broken. And in fact, we saw this NCQ scanning broken back in 2015 when we had the first PID flow study in Alice at round 1. And I think also later on, we also see the NCQ scanning broken at the top rig energy by Star and also by Phoenix. For me, let me see if I have the paper. Okay. So in principle, there's a paper which we cite in this JHAP paper from Wenbin Zhou and together with Shenlian. And it's a co-LBT calculation with hydro plus coalescence plus fragmentation. So if you only have the contribution from let's say quark coalescence, right? Then the V2 in the final state is roughly 3 versus 2 for baryon and meson, and only roughly. But then what really happened is in that calculation, they also have a hydro calculation which extended a little bit. So the hydro will not completely disappear, but it's getting smaller and smaller contribution if you go to high PT. And then whenever have a hydro contribution, and the hydro results cannot be scaled 3 over 2 for baryon and meson, right? And in fact, baryon V2 is larger than meson V2 from hydro because of the mass effect. So if you combine the results of hydrodynamics plus quark coalescence, you would expect that NCQ scanning should be broken. And if you go to slightly higher PD, it's slightly different. So if you go to higher PD, let's say about 5 GeV, okay, now hydro disappear. And what happened is a jet fragmentation, right? And for jet fragmentation calculation, if you trust the co-LBT, they predict pion, kaon, proton V2 are the same. And there's no particle species dependence for the particle energy loss. Therefore, the V2 are the same. And then if you think about the contribution from coalescence, it's 3 versus 2. And if you think about jet fragmentation, it's 1 versus 1. If you combine them, it will be diluted, right? So it'll never be 3 versus 2, either at low PT or at high PT. And this is my understanding. And remember, when we are talking about NCQ scanning, it's a very rough scanning until in a very narrow PT window, let's say. So if you look at the LHC, when we do the scanning and when we do the ratio between different particle species, the deviation is not better than 20%. In the sense, the best place, the best PT range, the deviation is roughly 20%. And for lower PT and higher PT, it's more than 20% deviation. So that's what basically we see and what I understand.
Okay, thank you.
Any further questions for you?
So I am Zhou. So I have the question on slide number 26, the slide in which Yuri was asking, slide 26.
26?
Yeah, so this W parameter, is it related to the smearing at the initial stage? I mean, in hydro calculation, in order to get a smooth profile at initial time tau naught, we do a smearing. Is this W related to that?
So this W is the nuclear weight that you put, right? And in principle, this is a parameter that can be constrained by the DIS memories. For example, they have a chip side production in Kira that can constrain the parameter, and I believe IP plasma using a very small nucleon width because they try to fit the HERA data. This is really the initial condition, had nothing to do with QTP evolution. I answer the question.
Okay, thank you.
Yeah, so on this slide, I have one question. So since you see that this W parameter has this sensitivity, I mean this nucleon size. So is there any kind of similar measurement can be done, for example, in p-lead collisions where you have this nucleon hitting on the lead?
Excellent question. I actually don't know because so the p-lead, I can say we do have the p-lead results in both ALICE, ATLAS, and MCMS. But for the model calculation right now, so the model calculation with IP plasma is not very well describe the data. So in that sense, when the model is still failed, it will be rather risky to draw a strong conclusion out of such a comparison, right?
Okay, so so my question is also, I mean, another question is there any ALICE measurement that has done this kind of Pearson correlation measurement in PA collisions or like in small systems?
Yes. So we actually have preliminary results for PP, and I think we are finalizing the paper also for p-lead. So it will be, let me see if I include it here. Yeah, some of these have been approved in 3 or 4 years, 3 years ago perhaps. And right now we are also preparing the paper with the p-lead results.
Okay, thank you.
Okay.